Okay, more generally than in the preceding. Now in the preceding we showed that if we take this set of vectors in R2, we form a linear combination of these vectors that's equal to 0, answering the question, are there linear combinations that are equal to 0? This is equivalent to the matrix equation. This matrix equation is equivalent to a set of two simultaneous equations, a system of two simultaneous equations. And that system is equivalent to the augmented matrix we see here. We solve by row operations. We find that we end up with a free variable. We let C3 be the free variable, and let C3 equal T. Then we get C2 and C1, and we form those into a column vector for the three constants, for our three constants, C1, C2, and C3. And we find there are infinitely many linear combinations equivalent to, T times these three numbers, which is equivalent to T times these three numbers with just a different value of T. If T is 7 times as great, then we have these three numbers. Okay, so any multiple of these three numbers gives us a linear combination C1, C2, C3, which when multiplied by these vectors in turn gives us a 0 vector. And we call this system a homogeneous system because we have zeros here. Okay, so the more general question can be written almost identically to what we just did. Now I'm not going to work it out in general. I'm not going to give you specific vectors now, but our homogeneous equation that comes from this question, can a linear combination of this set of vectors equal 0, is C1 V1 plus C2 V2 up through Cn Vn equal to 0. And we could write that compactly in matrix notation as the matrix whose columns are your vectors V1 through Vn times the column vector C1, C2 down through Cn equals a column of zeros, and there are as many zeros here as there are numbers in each of your vectors. So if your vectors all have length 4, then you're going to have 4 zeros here. If the vectors have length 292, then there are going to be 292 zeros here. And of course your matrix is going to have 292 rows, which you should fully understand by now. If you don't, you need to go back and review the last few videos. Okay, so there's your equation. And it can be then expressed as don't know why I'm leaving myself all that room. I'll express it more compactly as this, where the 0 vector is the 0 vector, same dimension as your numbers, vectors here, same length. Okay, so if the length of your vectors is m, then this is a 0 vector with m zeros. And this is an m by n matrix. We can solve by reduction. Or by row operations. And if we get free variables, we get infinitely many solutions. Now you might or might not be at the stage where you understand that, but what I'm about to say, but if you have one free variable, you get a one-dimensional subspace or subset of solutions. If you have two free variables, you have a two-dimensional subset of solutions. And these are solutions of the homogeneous equation. And we can say that the solutions form the null space of the matrix. And of course, if the matrix represents a linear transformation, if you've by this point seen linear transformations, then that's the null space of the linear transformation. Put that in parentheses because we can do the null space of the matrix before we do the null space of the linear transformation. But if you know about linear transformations, then you know that linear transformations can be represented by matrices, and the null space of the linear transformation corresponds to the null space of the matrix, which corresponds to the solutions of this equation generally obtained by reducing the matrix.